No,
Okay.
that's not later.
Okay, so this was a study made with my student Martin Jutsi, who is here, and I will speak because Martin was away for some time and had to defend his thesis, etc. It's not that the boss speaks for the students like this. So that was a collaboration with the University of Nice and University of Bern, where there is Professor Willy Benz and Marco Delbo also in Nice contributed. So the aim is to determine the disruption energy threshold for asteroids, which means what is the impact energy that you need to break a body. I will come later to the real definition. So first of all, concerning the asteroids, they have wide sizes, shapes, and physical properties. And that, of course, is a problem because, of course, collisional response depends on these physical properties. And moreover, something very important for the collisional response is that we have evidence that several of them have a high degree of porosity. So not only they can be large blocks with different shapes, but also the porosity inside can be different. So in the framework of the design of the deflection mission, it is important to determine the impact response of a small body to make sure that you will achieve a deflection and how efficient it is. So just to show you a different example, you can see from only 3 pictures that you really have things very different, like the asteroid Matilda, which is a C-type, so it's carbonaceous-like object with low albedo, and the bulk density was measured by the flyby of the NEAR spacecraft, and it was found about 1.3 grams per cubic centimeter, so very low density, and it's a 50-kilometer object. On the other hand, you have asteroid Tokawa, which is only 500 meters in size, and you can see that it is what we call a rubble pile, which means blocks connected together with gravity despite their very low size. And this is also consistent with the fact that the bulk density is only 2 grams per cubic centimeter, while the spectra, which correspond to ordinary chondrites, suggest that corresponds to about 40% porosity inside. And then you have comets, which of course are even more, have a lower density. So just on these 3 images, you can see that you can really deal with very different things. And good luck to deflect something like that. And despite that, we know also, and that's also good, that several of them come from the main belt. Most of the NEOs come from the main belt. And this shows you a diagram, say major axis, so distance to the sun, and eccentricity. And this is the Earth crossing line, Mars crossing line, Venus crossing line. And several years of studies of celestial mechanics show that most of the bodies, main belt bodies, come from resonances which increase their eccentricity so that they can reach the Earth crossing zone. And most of them actually go into the sun only on a few million year time scale. This is the times going. And the lucky ones are extracted by encounters with planets and from the resonance, and so they can go down and evolve as NEOs. And the median lifetime of this population is about 9 million years, despite the fact that they are in a steady state. The reason why they are in a steady state is that because collisions and other mechanisms occur in the main belt during this evolution and replenish constantly the population. So these are the population we have to deal with. So there was already some deflection projects which were studied in ESA, like the mission Don Quixote, which led to 3 phase A studies where final extension was in April 2007. And so the aim was to send 2 satellites, one going into orbit around an asteroid and another one coming 6 months later, making an impact, and the first one would measure the deflection. So that's something that in any case should be done, even if we can try to model this. We need to confront to some reality and check that our models are valid. So a question often asked, and that's also true, I was on TV again last Saturday, and the question which is asked by the public is, well, but if you make a deflection, how are you sure you will not just break the body? And so that we just deal with many fragments which still come on Earth and you don't solve the problem. So in order to answer to this question, what you need to know is what is effectively the threshold of impact energy which leads to a disruption rather than a crater. And that's what the aim of this project. So there was already a study made by Benz and Aslog about that. So what we call the impact energy, specific impact energy, is the kinetic energy of the projectile divided by the mass of the target. And we define Q star as this threshold for disruption, and the definition is that Q star corresponds to the energy which leads to a larger fragments which contain 50% of the mass of the parent body. So if you have more than 50%, you are in a cratering regime. If you have less than 50%, you have a disruption regime. And the study was made by Benz and Astrog on basalt targets. And they found that you have two regimes in this diagram. So this is the impact energy you need with respect to the target radius. And you can see that there is a regime where when you increase the size of the target, the impact energy that you need to break it decreases with size. And the reason is that the larger a rock, that's what we know, the highest probability you have to have large cracks inside. And so since you have already large cracks inside, they are weaker. And the length of the cracks increase with the radius of the target. So they become weaker. But then, so that's called the strength regime. And then you have another regime where the impact energy that you need increases again, and this is because gravity starts to be an important contribution. So you not only have to fight against the strength, but you also have to fight against gravity. And of course, gravity increases with the size of the body, so that when it is negligible, it doesn't count, but then here, the impact energy increases because you have this gravity which comes into play. So the project was to revise with an improvement of the fragmentation model to check this curve even for basal target, and also to look for this Q star for other material properties. So how do we simulate catastrophic disruption? So as I said, you have two regimes, and more importantly, the gravity regime, you first have to compute the fragmentation. So for this, you have a hydrocode that we call an hydrocode, which computes the hydrodynamical evolution, so the shock wave propagation. And this is associated with a model of material failure, so like brittle failure, for instance. And then once the cracks have been propagated and you have fragments, these fragments can be massive enough to still interact under the gravitation. And in order to follow this phase, which is still part of the collisional process, you need to compute that with n-body code. And of course, since we have thousands of fragments or even millions, you need to have some kind of efficient way to compute that. So I will come actually into the details of the fragmentation model later during the detailed presentation. But just to show you a few moves, so this is, for instance, a target target of 25 kilometers in size impacted by a projectile, and you see how the damage propagates into the target when you impact the projectile. So and of course you can have different kind of targets, and one in particular, the very important thing in this process is what is the internal structure of the body, because of course the damage propagation will not go the same way depending on the internal structure, and you can have a wide variety of structures. This one comes from, guess who, Martin, who is a Swiss. So Swiss cheese represents kind of well a solid rock with large voids. So everything is solid here, you don't have porosity, and the porosity is due to the large voids which are here. And then this is a purely solid rock, so no porosity, really bare rock. And then of course you have porous and crushable, rubble piles, reaccumulated large blocks, and then reaccumulated small blocks. And of course, the propagation of the shock wave which will be affected differently based on the material properties here. So the impact response will be different, and that's what we need to determine. So just to show you an example, Martin developed a model for porous bodies, which is actually the first model of fragmentation for porous bodies that was developed and validated with laboratory experiments. I will show you that in the detailed presentations. But you're going to see the difference of response from the two bodies. So these are movies made by Martin where you have here same initial conditions, same impact conditions. The only difference is that here the body is porous, microporous. I will come to the definition later. And here, no, this is non-porous, so basalt, and here it is porous. But still, the bulk density is the same. Huh? So it's just the presence of porosity that will make the difference. So in the non-porous case, you see how it fragments it, so you disperse kind of fragments. In the porous case, however, you actually make compaction, like if you were pushing in the material. So that's something which is not very good for deflection, because the deflection efficiency depends on the ejecta of the crater. In this case, there are not much ejecta, you just push inside. So the momentum transfer may be a little less high in this case.